Hello everyone, I am Dr. Sudhan Sharma from School of Computer and Information Sciences, Indira Gandhi National Open University, and this session is about important kind of concepts of calculus. This is in fact a conclusive session wherein we are going to recall and remind that what important concepts we learned till the moment in block number 3. The block number 3 was comprised of several components, be it limits and continuities, differentiation, application of derivatives, integration and application of integral calculus. We had explored ample number of numericals to understand various concepts given in block number 3. You need to understand that block number 3, which is calculus, is very important from every domain of computer science, be it data science or machine learning or artificial intelligence or optimization techniques, wherein excessive use of calculus is being made. However, you can apply the concepts which are delivered in the sessions for block number 3 to other domains of say social sciences or even management and many more, what to say. So, just to recall what we had learned till the moment, we understood what is limits and functions, limits and continuities. We understood how functions, limits and continuities are related to derivatives and how differentiability is affected by evaluating the continuity. Apart from this, we understood what are the rules of differentiation and learned how to determine the derivative of exponential and logarithmic function. We understood about the chain rules and perform the differentiation of parametric form and also learned how to determine the second order derivatives. So far as the application of the derivatives is concerned, we learned about the calculation of rate of change of one quantity. Apart from this, we understood also that if we know the rate of change of one quantity, then how to find the relative rate of change. Apart from this, we understood when a function is increasing or decreasing and how to determine the maxima or minima of a function. So far as integration is concerned, we understood what is antiderivative, how integration and differentiation are related to one another. We had compared the formulas for differentiation and integration and used the table of integration to determine the antiderivatives of some of the simple functions. Further, we extended our discussion of integration and understood how to perform integration by substitution, how to perform integration of rational functions, what is integration by parts, rule of Eilert, and apart from this, we extended the understanding of integration to apply the integration and determine the area under the curve and length of the curves. These are some of the very important topics which had covered in our past sessions for block number 3, that is calculus. So, the very first thing was limits, wherein we understood that if a function f is tending to value L as variable x is tending to value a, then this expression should be expressed as limit x tends to a f x is equal to L. We proved an important formula, that is limit x tends to a, limit x tends to a, x to the power n minus a to the power n upon x minus a is equal to n a to the power n minus 1. So, we applied this formula also, and this formula is very important. Apart from this, we understood what do we mean by left hand limit and right hand limit, how this concept of left hand limit and right hand limit is used to establish the continuity of the function, and we learned that left hand limit is represented by limit x tends to a minus and right hand limit is represented by limit x tends to a plus. Both should be equivalent to L, value L, that means limit x tends to a f x, in order to establish the continuity. So, left hand limit should be equal to right hand limit. We solved some numericals, likewise one shown over here, where limit x tends to 0, modulus of x is over x is required to be shown that it does not exist. We performed the steps and we applied the understanding that modulus of x is equal to x when x is greater than 0 and minus s of x when x is less than 0, greater than equal to 0 and x is less than equal to 0, less than 0. So, that means for function f x, modulus of x upon x, modulus of x upon x will turn out to be 1 when x is greater than 0 and will turn out to be minus 1 when x is less than 0. So, you can say that when limit x 0 plus, that means when a value of variable x is greater than 0. So, towards the right hand side, we are going towards the right hand side, that is positive part. So, limit x tends to 0 plus f x turns out to be value 1, and when we are evaluating towards the left hand side, that is on the negative region, then limit x tends to 0 minus f x turns out to be limit x tends to 0 minus 1, that is minus 1. And we found that left hand limit is not equal to right hand limit, one is plus 1 and other one is minus 1. So, the limit x tends to 0 f x does not exist. We understood that what continuous functions are, and there are three important conditions to establish that a function is continuous. That means a function f is said to be continuous at x is equal to a if these three conditions are satisfied, that is function at point a should be defined and limit x tends to a f x should exist and limit x tends to a f x should be equal to f a. Then we extended our discussion towards the establishment of the relation between limits, continuity and the differentiability, and the differentiability, that is dy by dx, or you can say d dx of function f x, can always be written as limit delta x tends to 0 f of x plus delta x minus f of x divided by delta x. This is nothing but f dash x, and you can always say d dx of f x is written in terms of limit. This is the fundamental definition of function when it is differentiable. And a very important statement was discussed in the respective session, that if a function is not continuous at x, then function is not differentiable. That means differentiability and continuity goes hand in hand. We solved several numerical by using the fundamental definition of differentiation, that is delta x tend to 0 f x plus delta x minus f x upon delta x, and we found that how to use the concept of the limits to find the differentiation by using the concept of first principle, which is the limit x tend to 0 f x plus delta x minus f x upon delta x, which is nothing but d dx of f x. So far as the rules of differentiation are concerned, we explored an ample number of rules, that derivative of constant is equal to 0, scalar multiple rule, wherein a derivative of a constant into function is equal to constant into derivative of that function. We have sum rule, wherein we understood that derivative of sum of two functions is equal to sum of the derivatives of independent functions, and difference rule, wherein we understood that derivative of difference of two functions is equal to difference of the derivatives of the two respective functions. We also understood about the product rule, that is d dx of f x into g x is equal to f x into g derivative of g x plus g x into derivative of f x, which is this expression, and this is nothing but your product rule. We explored the power rule also, wherein we the expression d dx of x to the power n is actually n x to the power n minus 1. And the reciprocal rule, which says that d dx of 1 over f x is equal to minus of f dash x upon f x square. We solved ample number of numericals for these rules. The quotient rule was quite important, and you need to understand the sequence of performing differentiation. The denominator function into derivative of numerator function minus numerator function to derivative of numerator function upon numerator function square will be equal to d dx of f x by g x. We also understood that d dx of e to the power x is equal to e to the power x, and we extended our discussion when we were understanding the concept of the chain rule, and we understood that dy by dx can be written as dy by dt or du into du by dx. So, this type of functions were explored when the function is function of another function, say that means ddx of that fx is function of another function gx. So, in that case that means you are supposed to find derivative of that function into g dash x, that was nothing but dy by du, the dy by du and into du by dx. So, you can say that we differentiated the function with respect to gx, which can be written as u, and differentiated g with respect to function x. So, the chain rule can be extended by this expression also, that dy by dx can be equal to dy by du into du by dv into dv by dx. So, you can recall that these things got cancelled out. So, this is how the chain rules actually work, and we solved ample number of numericals. We also learned how to determine the second order derivative and how the concept of first order derivative and second order derivative are used to find whether the function is increasing or decreasing. And we solved ample number of numericals, and under the section wherein the application of derivatives were discussed, the first important application was to determine the rate of change of quantities. So, we understood that the rate was changed with respect to the time. So, dy by dt, that is variation of a function with respect to time, can be expressed as dy by dx into dx by dt. This is the application of the chain rule. Now, this formula, this expression can be interpreted that if we know the variation of one variable with respect to time, and we also know the variable of other variable with respect to time, and we want to know how one variable varies with the variation in other variable, then we can use the chain rule, and we can find that dy by dx can always be written as dy by dt divided by dx by dt, wherein dy by dt and dx by dt are rate of change of two variables, and dy by dx is change of one variable with respect to the other variable. We understood how to determine whether a function is increasing or decreasing, and there were two criteria, that if in an interval x1 is less than x2 and fx1 is also less than fx2, then the function is increasing, fx2 then the function is increasing. But in case if x1 is less than x2 but fx1 is greater than fx2, then the function is decreasing. So, we learned these concepts. Apart from this, we learned what maxima and minima of a function means, and we learned that if fc, where c is the value which is belonging some interval I in which the function f is defined, then the value of function at point c given by fc is absolute minimum if fc is less than or equal to fx for all values of x in I. Similarly, fc is maximum or absolute maximum if fx is greater than equal fc is greater than equal to fx for all values of x in I. So, that means there is some point that might be either the minimum for all the values of x or maximum for all the values. So, say this is point c, this is point c, then the value defined at this point c is of function is fc. So, within the interval, if fc is greater than fx, if fc is greater than or equal to fx for all values of x belonging to I, then for all values of x belonging to I, then that point is maxima. So, this is all what we learned about maxima and minima, and we also performed and applied the first derivative test to determine local minima and local maxima, wherein we learned how to determine the critical point, critical number, and if the derivative changes the sign from positive to negative at point C, then point C is referred as local maxima. Also, if the derivative changes the sign from negative to positive at point C, then FC is called the local minima. So, by figure you can say that in this region the derivative of function x is greater than 0, the slope is on the rising side, and in this case the slope is on the falling side. So, f dash x is less than 0. So, sign is changing from positive to negative. So, this is the maxima part. So, this is the maxima part, and over here the slope is on the falling side and this is on the rising side as x is increasing. So, sign is changing from negative to positive. So, that means this is the minima part, this is the minimum part, because the sign of the derivative is changing from negative to positive, and that is why f c is the local minimum. And in the second derivative, we understood that there are situations wherein the complexity of the first derivative test was that we need to find that the sign is changing from positive to negative or negative to positive. So, so this was somewhat problematic. So, in order to simplify that, we use the concept of the second derivative test, and the second derivative test says that if f dash c is equal to 0 and if f double dash, that is double derivative of the function at that point C is positive, then the local minima lies at point C. Local minima of the function lies at point C. So, f c represent the local minima, and if f dash c is equal to 0 and if f double dash c, that is second derivative of the function at point C, is negative, then function f c is the local maxima. There are situations wherein the second derivative test fails. We discussed that situation, that in case the f dash c is equal to 0 and f double dash c also turns out to be 0, then second derivative test fails, and in that case we are supposed to perform the first derivative test. So, we discussed about the basic integration rules, and these were the rules which are compared with the differentiation and the integration. So, we compared the formula for differentiation and integration, and we find that integration is opposite of differentiation and differentiation is opposite of integration, and that is why for integration we also use the term antiderivative. We learned about what is the general pattern of performing the integration, and wherein the steps are that we need to rewrite the given expression, then integrate and simplify the expression, and ample number of numericals were solved. This was one of the numerical which was solved, and we exhibited how to rewrite, integrate and simplify to perform the integration. Thereafter, in our earlier session, we discussed about the integration by substitution, and we understood how to exercise this practice of substitution to simplify the complex terms into the simpler integrations. Likewise, over here, integral of e to the power x into e to the power x plus 2 to the power 7 integration is to be performed. Just to simplify, we replace e to the power x plus 2 by the variable t, and we got that e to the power x dx is equal to dt. So, e to the power x and dx, this expression was replaced by dt, and this expression was replaced by t to the power 7. So, the overall equation got resolved into integral of t to the power 7 into dt, and by using the power rule, integral by using the expression x to the power n dx is equal to x to the power n plus 1 over n plus 1, we got the expression t to the power 8 by 8 plus constant of integration, and substituting we got e to the power x plus 2 to the power 8 by 8 plus c. This is how we learned how to solve the integration by using the method of substitution. We also explored what are rational functions, and we also explored all the three cases for performing integration by using the concept of rational functions. We learned what are the proper rational functions and improper rational functions, and we learned how to transform an improper rational function into a proper rational function. Thereafter, we also learned about how to perform integration by parts, and we understood what is the rule of I late. inverse, logarithmic, algebraic, trigonometric and exponential. So, how to use this rule of Eilert to perform integration by parts, because this rule helps us to identify what is the first function and the second function. Because the integration by parts relates to the formula that first function into integral of second function minus integral of derivative of first function into integral of second function. So, if this is the expression, this is an algebraic expression and this is the exponential expression. This is the algebraic, and algebraic expression is turning before the exponential expression. So, algebraic expression should be treated as first expression and exponential should be treated as second expression. And now treating these first and second expression in the first function and second function, you can perform the integration as it was discussed in our respective session, and we got the integration to be x minus 1 into the e to the power x plus c. So, this is rearranged to this expression, and we learned about what definite integral is. Definite integral is an integral of the function f x which is defined in an interval a b, and you can evaluate the value to be f b minus f a. So, this is nothing but your definite integral, and we learned how to apply the concept of definite integral to find the value of the integral in an interval a to b. Thereafter, we also learned about the fundamental theorem of calculus, and we identified that how this fundamental theorem of calculus geometrically explains that that integral of any function represents the area under the curve, and also we learned that the derivative of a function and integral of a function are opposite of one another, and this theorem says that Ax is equal to integral of a to x ft dt, then derivative of Ax is equal to fx for all values of x defined in an interval a b. We solved the numerical and we understood that that if Ax is equal to a to the power a to x ft dt, then derivative of x is nothing but f of x. So, derivative and integral goes all together, both are opposite of one another. Apart from this, integral of a function, or rather you can say definite integral of a function, is representing the area under the curve, and we understood this, and area under the curve is represented by the definite integral. Likewise, over here the value of x is varying from the range a to b, and within this range the function f x is varying. So, this function f x is y is equal to f x. So, as a result of which the area enclosed by the curve will be represented by the integral I is equal to a to b f x dx, which is this expression. Also, we learned about how to determine the area between the two curves. Say we are given two functions f x and g x, which are defined in an interval a b such that f x is greater than g x for all the values of x between a and b, bounded by y is equal to f x and y is equal to g x. Then in the interval a to b, the area between the curves will be represented by definite integral of a to b f x minus g x dx. So, this area, this section, this shaded section represents the area between the two curves. We solved ample number of numericals to find the area between the two curves. Apart from this, finally, when this block 3 was concluding, the final unit, the final topic of the final unit for the application of integration was about the length of the curves, and the length of the curve was given by this formula, integral of a to b square root of 1 plus dy by dx whole square into dx, and which represents the length between the 2 points on the curve. Say this is point A on the x axis, this is point B on the x axis. Evaluating the value, we are having say f a and f b as the respective value for the function y is equal to f x at point A and B. So, the length between the 2 points A and B, length of the curve between the 2 points A and B will be given by a to b square root of 1 plus dy by dx whole square into dx. So, you are supposed to simply evaluate this definite integral and you can determine the length of the curves. So, these are all of them are very important topics, and I again advise you to go through the self learning material, ample number of questions, check your progress, and questions are given, solved numericals are also there. You can apply the understanding of the topics given in this session and solve ample number of numericals for better understanding. Thank you.